All right, let's sum up everything we are going to need to know about radioactive decay. We're going to cover alpha, beta, gamma, and the different types and general equations for those. What is radioactive decay? It's this process by which an unstable nucleus spontaneously disintegrates. It releases energy, it releases matter. So this nuclear decay process can be natural or can be induced artificially. In either case, when a nucleus decays, radiation is emitted in the form of particles. Those are particles that have mass. Photons, think of just packets of energy. We see that when we talk about gamma radiation, or it could do both. Now, the nucleus before the decay is going to be called the parent, and after we're going to call the daughter. So you might hear me refer to as the parent nucleus or parent atom, or daughter nucleus and daughter atom. Three main types here are alpha, beta, and gamma. Alpha particles are basically a helium nucleus. The helium nucleus has an atomic mass of 4 and an atomic number of 2. In the case of alpha particles, there are no electrons. It's just the nucleus. Beta particles are either electrons or positrons. Remember, electrons are negative particles. Positrons are basically the opposite of electrons. They're positively charged particles with a mass equal to that of electron, but their charge is opposite than electron. Gamma rays are high energy photons. It's pure energy. We're not going to be measuring any mass. We're just going to be measuring energy on that type of radiation. So here we go. Alpha decay, it is the weakest or the least dangerous, I should say, of all the ionizing types of radiation. Now, not all of your isotopes do decay, but of the ones that decay, alpha is the most common. And it always involves the emission of a helium nucleus. That's 2 protons and 2 neutrons, and they're going to be decaying from that atom. How do we determine the daughter? To determine the daughter of the atom, simply subtract 2 from the parent's atomic number. This is the new atomic number. And subsequently, that's the identity of the new daughter atom. So to determine the daughter atom's atomic mass, you're going to subtract 4 from the parent's atomic mass. Let's show that in a general equation form. X is going to represent the parent atom and Y is going to represent the daughter atom. And the helium nucleus is our beta particle. So we generally notate that A is the atomic mass. That's the protons and the neutrons available in there. That's the total mass. And Z is the atomic number. That's the identity of the atom. That's the number of protons. So if you subtract 2 from the number of protons, you would go ahead and look at the periodic table. What's 2 less than X? Well, that's going to be Y. That's going to be our daughter one. And our daughter atom's going to have 4 less mass. Okay. Where does that go? Those numbers are accounted for. They're conserved in our alpha particle. So a couple examples, have your periodic table handy, and you want to show the chemical equation of the alpha decay for curium-248. So you're going to look on the periodic table and find curium-248. I'm going to go a little fast for you, so you can pause now at any time during the video if you want to check for yourself. But here's the solution to that. You've got curium, has an atomic number of 96. 96 protons become 94 protons, and that changes the identity of the daughter. We have to have 4 less of an atomic mass. And where do these numbers go? We account for them in the alpha particle. Our helium nucleus is going to be 4 and 2. Radium-223 is our second example we're going to show you. Radium is going to decay. It's going to lose 2 protons. So its atomic number is going to go down by 2. And it's going to lose a mass of 4. That mass of 4 is then accounted for in the alpha particle, the helium nucleus. So the helium nucleus has a mass of 4 and a number of 2. So just nuclear subatomic particles are involved in this. Electrons are not involved in this. Our alpha particles do not have electrons. They're just the nuclei of helium. All right, beta decay. Beta decay transforms neutrons and protons in the nucleus. We're going to look at three main types of beta decay, and they all involve the emission of a beta particle. A beta particle is going to be a negative electron, or it's going to be a positive positron. And I might have to skip through some of these because they talk about neutrinos, and I don't want to get too complicated in it. I want to focus on the products of the equation here. So there are three main types of beta decay. They all involve the emission of a beta particle. Beta particle is going to be either an electron, which is negative, or a positron, which is just like an electron, but positively charged. So let's first look at beta negative decay. In the beta negative decay, the parent atom emits an electron. This is from the nucleus. This is different than what we were previously learned about where our electrons go, okay? So we are very comfortable with an electron being removed from the orbit of an atom and giving an atom a positive charge. But it turns out there can be electrons emitted from the nucleus. If things get a little too tight inside the nucleus, they're going to have to kick something out. So if the atomic nucleus contains too many neutrons, there's a strong nuclear force, and that becomes much stronger than this electrostatic force, which is the attraction of the positive and the negative. The strong nuclear force is too much for the atom to handle. It's going to want to break apart. So it needs to maintain stability. It's going to spontaneously decay into a proton and an electron. So the proton is going to stay in the nucleus, and it's going to increase the mass. It's going to increase the atomic number, but not the mass. So the electron is just going to be ejected from the nucleus. So proton's going to stay in the nucleus. It's going to give us a larger atomic number, or the identity, right? But the mass will not increase. The electron is going to be the beta particle, and that's just going to be yeeted out of the nucleus. Let's take a look at the general equation here. X is going to represent our parent atom, and Y is going to be our daughter atom. Since we are beta decay, what we're doing is we're gaining a proton and losing an electron. In beta negative decay, we're gaining a proton, we're losing our electron. Our mass stays the same. So our A value stays the same. Let's do two examples. Let's show beta negative decay of sulfur 35. Notice how sulfur 35 starts out with 16 protons, but when you add a single proton, now it changes the entire identity of the atom. The atom still maintains an atomic mass of 35, but now the daughter atom is chlorine plus a beta particle. A beta particle is simply a negative electron. The electron is essentially massless. So we're going to indicate a 0 there to show that it's massless. And it has a -1 charge. So that's why that's notated like that. Thorium 234, it's going to break down and change into from its identity number, from its proton number of 90 to 91. The 234 is conserved, the mass stays the same. No mass is ejected, but a negative particle, an electron, is ejected. You can probably guess that beta positive decay is going to be similar. In beta positive decay, we're going to yeet a positron from the nucleus. So similar to beta decay, similar to beta negative decay, beta positive decay, a nucleon is undergoing transmutation and an ejection occurs. That's a fancy way of saying that particles inside the nucleus can change and get yeeted. A proton, in this case, changes into a neutron and a positron. A proton changes into a neutron and a positron. So the positron, which is like the opposite of an electron, is a small positive particle gets ejected. Since it's a small positive particle, we're going to negate any mass on it, and we're going to know that it has a +1 charge. The positron is ejected from the nucleus, and the neutron remains in the nucleus. So atomic mass does not change. Atomic mass stays the same, but now our atomic number is decreased by 1. Our atomic number is decreased by 1. So we have another identity for the daughter atom. So our parent changes. We'll look at sodium and calcium real quick. A general equation is going to be your parent mass and parent atomic number gives you your daughter with the same mass, but 1 less proton or 1 less atomic number. In addition to that, it's going to yeet a positive particle with no mass called a positron. All right, so if you have your periodic table, you try this, you look at the isotope of sodium-22. Sodium has an identity, an atomic number of 11. But if you take one of those protons away, you're left with neon. The mass stays the same, but we emit a positive particle, a positron. Calcium is going to transmutate into the daughter atom of potassium. And we're losing a proton and we're ejecting a positron. Beta positive decay ejects a positron, beta negative decay ejects an electron. And as it turns out, there's another way that electrons are involved in here, and we're going to call that electron capture. In electron capture, it's a type of beta decay, but there's no particle ejected. So an electron capture is a different type of beta decay in which no particles ejected from the nucleus. So instead, the nucleus is going to grab, it's going to give a big squeeze, nice hug to the electron. The nucleus is going to capture an electron and it's going to combine with that proton, and it's going to make a neutron. Let me say that one more time. An electron gets captured by the nucleus, and that negative electron forms with the positive proton to make a neutron. Atomic mass remains the same in this case, but atomic number goes down because we've lost that proton. That proton has now been changed into a neutron. So when you capture an electron, your atomic mass stays the same, but your protons go down by 1. Let's look at the general equation for that. We've got our parent, X, has a mass number and an atomic number. Let's add an electron to that nucleus. And what do we get? We get 1 less proton, same number of total neutrons, same mass number, I should say. So 1 more neutron, but the mass number stays the same. It's just been transmutated. I'll do 2 examples, potassium and carbon. On your periodic table, look at potassium-40 isotope. That means it has an atomic mass of 40. Potassium has an atomic number of 19. Add an electron to that nucleus, and you have got yourself argon. Okay? If you add an electron to that nucleus, you're going to change the nucleus. Now it has 1 less proton, so its atomic number becomes 18. In carbon 11, that atomic number of 6 becomes 5. Okay, and again, our masses stay the same. And that's electron capture. Quickly look at gamma decay and give you guys some examples. Gamma decay usually happens after, okay? And after an atom undergoes alpha or beta decay, the daughter nucleus may do gamma decay, because gamma decay happens when you're in a high energy state. So you're excited. The excited nucleus is going to spontaneously emit a gamma ray. So it's too excited. It's not stable. It needs to get rid of some of that energy, and it's going to do that in the form of a photon. If it does that, it can move to a lower, more stable energy state. Okay. The photon itself doesn't have mass. It doesn't have charge. It's just raw energy. So the parent atom and the daughter atom are the same, but they're going to be in different energy states. And what I'm going to do is just use an asterisk to show you which state of energy they're in. So general equation for gamma decay is going to show you a parent atom with an asterisk indicating that it's high energy. When it goes to low energy, we're going to add a photon. We're going to add gamma particle. No mass, no charge, 0, 0 for that. Here's 2 examples. Let's check out dy on a periodic table. Atomic number 66. The isotope 152 tells us the mass number is 152. Since it's excited, we're going to keep the asterisk. When it decays, we leave the asterisk and we write the lowercase Greek letter gamma. It looks like a little sideways capital cursive L, or almost like a V with a loop down there. Let's look at curium 244. When that stabilizes, it releases its energy. Its gamma radiation is released. So think of photons as pure energy or high energy. This is why like gamma radiation is potentially more dangerous to you because it's going to go through the skin, it's going to go through your tissues and into your organs and probably into your bones. Okay, I was going to stop, but let me just quickly do rules for the radioactive decay modes and show you a summary table. So you can use 2 rules to determine the unknown daughter atom when a parent goes under decay. First, you want to look at the total of the atomic numbers on the left, if it's the same as the total on the right, because obviously charge needs to be conserved. And the total of the mass numbers on the left is going to be the same as the total on the right, because all of the nucleons, the nucleus particles, protons and neutrons, that number needs to be conserved. So even though we have decay, we're showing that matter and energy are conserved. Now this table sums it up for us. I really like this table, so it's out of our book. I want to include it for you. Alpha, beta, and gamma. We're showing the symbols. Greek letter alpha shows a helium nucleus. We have beta negative and beta positive, and it shows an electron and a positron. And gamma, since it's simply going to be referred to as energy, we're just going to use the symbol without any particles. It's massless, right? What is it made out of? What's the charge? And then what happens to the parent? So quick sum up, in alpha decay, the parent does lose mass and you get a new element. In beta decay, the mass is conserved. There's no change in the mass number, but you also get a new element. So the identity of both alpha and beta atoms change. In gamma radiation, there's only energy loss. There's no change in the daughter, other than the daughters become more stable. And that should do it for us. Yeah. Let us stop.